Hello everyone, this is our video example related to the lecture where we talked about vapor-liquid equilibrium, but looking at just a single condensable component. And this is example 628 or question 628 from the textbook, page 332. So go ahead and look up that question, read it up first before you follow with this video. And this is actually an example that's pretty relevant to a lot of us, especially in the summer months, looking at how an air conditioner actually works. When we have the air conditioner going, it doesn't just cool the air down, it actually dries the air out a little so it becomes less humid. So let's see how it actually works down here. All right, in this question, it says on a hot summer day, the temperature is 35 degrees C, the barometric pressure, which is the atmospheric pressure, is 103 kilopascals, and the relative humidity is 90%. We have an air conditioner that draws in the outside air, cools it down to 20 degrees C, and then delivers it at a rate of 12,500 liters per hour. We are asked to calculate the rate of moisture condensation in kilograms per hour and the volumetric flow rate of the air that's drawn from the outside. All right, so here's a single unit with an air conditioner system, so let's draw that. We have our air conditioner right here. We have an outside air stream that's being drawn in, and this stream will be cooled down and some of the water vapor is going to be removed. So you're going to dry the air and cool the air down right here. We are given the temperature and pressure of the inlet air. And we are given the volumetric flow rate, temperature, and pressure of the outlet air down here. Actually, I'm going to call this stream 1, this stream 2, and this is our stream 3. So this stream 3 is our liquid stream, and this is our vapor stream right here. All right, so we're given the temperature down here as 20 degrees C. The pressure is the same. And our basis is given right here, volumetric flow rate of 12,500 liters per hour. All right, so that's all the information we're given. We have a relative humidity of 90% down here, which we'll eventually use, but let's just put it down here. Relative humidity 90%. In terms of all the other variables, we have nothing, so let's go ahead and finish labeling up this process flow diagram. So we know that in the inlet part down here, we have both dry air and water vapor. So we're going to call this as the molar flow rate. And then we have our water. And BDA, recall BDA means bone dry air. We're just separating the air with the water vapor within our air stream right here. Same thing with our vapor stream down here. We have both components. So we have N2, we have the water vapor, and we have the bone dry air. Down here, in this case, under these conditions, our bone dry air is not condensable. So the only thing that condenses out here is our water vapor, or water. So we have an N3 down here. And this is all water. So we don't need any compositions right there. Okay, once we have this, let's circle our unknowns. And let's go ahead and try our degree of freedom analysis. So in this case, our DOF is 7 unknowns. So these are circled on the diagram. All right, the next thing we do is count the number of species. We have 2 species, which is our water and bone dry air. We have 2 constraints, so sum of y equals to 1 in here, sum of y equals to 1 in here. All right, so now we have everything that we have done so far is the same that we have done before, number of species, number of constraints. The last thing we need are our physical laws, and in this case, we know that we can solve this problem, which means we actually have 3 laws. Or at least we need 3 laws to be able to solve this problem. So what are the 3 laws? Number 1 is using this relative humidity spec. With this relative humidity, what you can do is actually convert it to a partial pressure. With the partial pressure and the overall pressure, you can use Dalton's law to convert it to our mole fraction. So in this case, we do have Dalton's law in 1. And the way Dalton's law is going to work is you're going to get from your relative humidity to your partial pressure of water to eventually your mole fraction of water right here. Okay, then we have, in this case, vapor-liquid equilibrium for our water in streams 2 and 3. So we have one Raoult's law. And the last thing we have is our ideal gas law. We have the temperature, pressure, and the volumetric flow rate. So we can use our ideal gas law to figure out our molar flow rate. And with that, 7 minus 2 minus 2 minus 3, this is how we get our 0. And so we're going to solve for our 7 different unknowns with this 7 different equations that we have listed out down here. So let's go ahead and try that. So here's our diagram and our degree of freedom analysis that we have derived. So let's start to now solve this problem. And we're going to start by using the 3 laws that you see down here in our degree of freedom analysis. Let's start with the new one, which is our Dalton's law. But first, we need to use the idea of relative humidity, which we introduced in the lecture. So the definition of relative humidity is the partial pressure of your water vapor over the saturated vapor pressure or pure component vapor pressure of water at that temperature. And we are given that this is equals to 0.90 or 90%. Where are we going to find our partial pressure or our vapor pressure of water at 35 degrees C? In this case, you would look up table B3 for water. There's a tabulated table of values. We see that it is 42.175. So with that, we can just plug into the equation and we see that we have the partial pressure of our water vapor in stream 1. With the partial pressure of water vapor, we can now use Dalton's law to find the mole fraction because we have the overall pressure in that stream, convert it to the same units, and now we have our mole fraction as 0.0491. Use our constraint to find the mole fraction of our bone-dry air. We get 0.9509. Okay, so now we are done with one constraint. We are done with Dalton's law. We have the Raoult's law and the ideal gas law and our 2 species balances. So let's do the ideal gas law first. So that will be a review. In this case, we have, in stream 2, we know the temperatures and the pressures, and we know the volumetric flow rate. So using the ideal gas law, making sure that your units are consistent, we have N2 as 528.3 moles per hour. So now we are done with the ideal gas law. Let's go on to our Raoult's law, which is our vapor-liquid equilibrium for our water in stream 2 and 3. So Raoult's law for water, that's Raoult's law stated down here. But what you'll notice in this case is we have only one single condensable component. Only our water is condensable. The bone-dry air under these conditions is not condensable, which means in the liquid phase, we only have water. So if we look at what this value is, this mole fraction of water in stream 3 is just essentially 1 because that stream is all water. Okay, so we simplified our Raoult's law. And we can look up the pure component vapor pressure of water at 20 degrees C, again from the table. Note, you can also use Antoine's equations to find that, but that's a lot more work. You actually have to find the equations, look up the constants. So remember, for tables, you always, for water, you always use the tables rather than Antoine's equations. It will save you a lot of time. Okay, so once you have that, we can put in the numbers and find the mole fraction of water vapor in stream 2. With that, we have our constraint, and we have our mole fraction of bone-dry air as 0.9773. The last thing we need to do is our 2 species balances. So let's start with our bone-dry air balance. The reason why I picked bone-dry air as my balance is because you realize that in stream 3 there isn't bone-dry air. So generally, you pick the species where it has the least number of terms. In this case, if you write out the bone-dry air balance, you realize you only have one unknown left, which is N1, so we can solve for that. Once we have that, we can use the overall balance, solve for our remaining unknown, which is the amount of liquid that has condensed, and we have 14.7 moles per hour. All right, we have solved for all the unknowns. Let's actually answer the question. It asks for the rate of moisture condensation. So rate of moisture condensation in kilograms per hour. We already have it in moles per hour, that is our N3. So to convert from moles per hour to kilograms per hour, we need our molecular weight of water. So we just multiply by that and we get 0.265 kilograms per hour. The last one is asking for the volumetric flow rate of the air drawn from the outside. So this is simply using our ideal gas law in stream 1. We have the molar flow rate, N1, that we found. So we have the pressure and temperature. We just use our ideal gas law. and we can find the volumetric flow rate as 13.5 meters cubed per hour. As always, go ahead and practice the ideal gas law, especially with the units. Make sure that you understand how to make the units consistent so that you can actually get the correct answer here. Alright, so that's all we have for this example. There will be one more video example on a single condensable component, and that will be the end of our material balance part before we move on to our energy balance. So work hard, be smart. I'll see you then.